Hello there, and welcome to the Sleepy Space channel. There is not one kind of black hole, but many, and they could hardly be more different from one another. Some are the collapsed remains of a single dying star, no wider than a city, yet holding the weight of several suns. Others are the great dark giants at the centers of galaxies, larger across than our entire solar system. Some may be older than the first star, born from the raw unevenness of the newborn universe. And some, stranger still, exist only in the equations, from mirror-image white holes to the exposed singularities that nature may forbid. Tonight, we move slowly through every kind of black hole there is. If you find these slow journeys through the universe worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is anything you need to hold. There is nothing here to solve, and nowhere you need to be. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade quietly away. Let's begin. A black hole is not really an object at all. It is a condition, a state that space and matter can fall into, the way water can fall into the state of ice. Every black hole in this survey, no matter its size or its story, is the same condition reached under different circumstances. Before we walk through the many kinds, it is worth understanding the few features they all share, because once these are clear, each type becomes a familiar shape seen from a new angle. The condition begins when matter is packed together so tightly that gravity closes over it. Gravity, at ordinary scales, is the gentlest of the forces. It holds us to the ground and keeps the planets in their long, slow circles. But gravity has one quality the other forces lack. It only ever pulls, and it never tires, and given enough mass in a small enough space, it can overwhelm everything set against it. When it does, it draws a boundary around itself, a surface of no return, and the region inside that surface is sealed away from the rest of the universe. That surface is called the event horizon, and it is the defining feature of every black hole. It is not a wall and not a shell of any material. It is simply a location. The distance from the center at which the speed needed to escape becomes the speed of light. Since nothing travels faster than light, nothing that crosses inward can ever come back out. The horizon is a one-way door, and it is a very quiet one. There is nothing to see at the horizon itself, and nothing to feel at the moment of crossing. If you were to fall through the horizon of a large black hole, you would notice no barrier, no flash, no sudden change. The stars ahead would still shine. The dark would still be dark. And only later would you understand that the way back had closed behind you. The horizon is meaningful only from the outside, where it marks the edge of what can still be known. The size of that horizon depends almost entirely on the mass. More mass means a wider horizon. For a black hole holding as much matter as our Sun, the horizon would be only a few kilometers across, small enough to hide within a single city. For the great black holes at the centers of galaxies, the horizon can be wider than the orbits of the outer planets. The same condition, the same one-way door, but drawn at scales that differ by a factor of billions. There is a simple number that captures this, called the Schwarzschild radius. It is the size to which any amount of matter would have to be crushed in order to close a horizon around it. And here, the idea becomes almost humbling, because every object has one. The Earth has a Schwarzschild radius, smaller than a marble. A human body has one far smaller than a single speck of dust, smaller even than the nucleus of an atom. The reason we are not black holes is simply that nothing squeezes us that far. Only when great masses are compressed does the horizon grow large enough to matter. At the very center of the horizon, our present theories point towards something they cannot quite describe. The equations of gravity predict a place where matter is compressed without limit, where density climbs beyond any number, and the curvature of space runs to infinity. This place is called the singularity. In the simplest black holes, it is a single point. In spinning ones, it takes the shape of a ring. But most who study these objects do not believe the infinity is truly real. They read it instead as a signpost, a marker that says our understanding ends here, and that the true center waits for a deeper theory to describe it. What actually lies at the center of a black hole remains one of the honest mysteries of physics. Around a spinning black hole, space itself is set into motion. The rotation of the black hole drags the space near it into a slow swirl, the way a deep current pulls the surface of a river into turning. This region of dragged space is called the ergosphere, and within it, standing still is not possible. Everything must move in the direction of the spin, carried along whether it wishes to be or not. The ergosphere holds an enormous store of rotational energy, and that energy can, under the right conditions, be drawn out, which is part of how black holes come to power some of the brightest displays in the universe. The view from inside, for anyone falling toward a black hole, would be unlike any other sight in nature. As you fell, the bending of light would gather the whole outside universe into an ever smaller circle above you, its light crowding together and brightening near the edges. The stars would seem to bunch toward a single bright region, the way the world above the surface looks compressed and ringed when seen from beneath still water. Behind and around, the darkness of the horizon would spread and deepen until nearly the entire sky was black, and only a shrinking, brilliant window of the outside remained. It would be a fall not into fire, but into a gathering quiet, the universe folding itself into a single point of light. And it would be silent. Space carries no sound, for there is no air to carry it, and so the approach to a black hole would unfold in complete stillness. There would be no roar, no rush, no warning tone, only the slow rearrangement of light and the deepening of the dark. Whatever violence a black hole holds, it holds it quietly. The most extreme object in the universe makes no sound at all as it draws the world in. This silence is part of their strange character. Around a small black hole, this stretching becomes deadly long before the horizon is reached. Around a very large one, the difference near the horizon is mild, so that a traveler might slip across the boundary whole and only meet the stretching much later, far inside. There is a final quality all black holes share, and it is a strange kind of simplicity. Whatever falls into a black hole loses nearly all of its individuality from the outside view. A black hole made from collapsed stars and a black hole made from collapsed light would be indistinguishable if they matched in a few basic properties. The chemistry of what fell in, its color, its history, its shape, all of it, vanishes from the external description. What remains can be captured in only 3 numbers. How much mass the black hole holds, how fast it spins, and how much electric charge it carries. This surprising plainness is often summarized by saying that a black hole has no hair. There is nothing extra to describe. 3 numbers, and the object is fully known. There is one more shared quality worth dwelling on, and it concerns time. Near a black hole, time itself runs slowly, and the closer to the horizon, the slower it goes. This is not an illusion or a trick of the instruments. It is a real feature of the way gravity shapes the fabric of space and time together. To someone watching from a safe distance, A clock lowered toward the horizon would appear to tick more and more slowly, until, at the horizon itself, it would seem to stop entirely. This leads to one of the strangest sights the universe can offer, though it is a sight no one has ever quite witnessed. If you watched a friend fall toward a black hole, you would never actually see them cross the horizon. Instead, they would appear to slow as they approached, their motion stretching out, their image growing dimmer and redder, until they seemed to hang, frozen at the edge, fading slowly toward invisibility. From your distant vantage, they would never quite arrive. But from their own point of view, nothing unusual would happen at all. They would fall smoothly across the horizon in an ordinary moment, feeling no barrier, noticing no pause. Two travelers, two utterly different experiences of the same event, and both of them correct. The same slowing of time reddens the light itself. Light climbing away from a black hole loses energy as it struggles against the pull. And losing energy, it shifts toward the red end of the spectrum, and then beyond, into wavelengths the eye cannot see. This is why the region near a horizon fades from view rather than glaring. The closer to the edge a light source lies, the more its glow is stretched and dimmed, until it slips quietly out of sight. The horizon does not announce itself with brightness. It announces itself with a deepening, reddening silence. There is also a surprising order hidden in these objects, a link between black holes and the idea of heat and disorder. The area of a black hole's horizon behaves in a way that mirrors a quantity physicists call entropy, the measure of hidden disorder in a system. The larger the horizon, the greater this hidden content, and remarkably, a black hole turns out to hold more of it than anything else of comparable size in the universe. In a sense, a black hole is the most thoroughly scrambled object there can be, its interior beyond all accounting from the outside. This profound connection between the geometry of the horizon and the physics of heat is one of the most beautiful bridges in all of science, and it hints that gravity, space, and the flow of information are woven together far more tightly than they first appear. Those three numbers, mass and spin and charge, will guide much of what follows. They are the reason a handful of exact descriptions can cover every idealized black hole there is. But the most immediate way to sort these objects, and the one that shapes everything else, is the first of the three. It is simply their mass. And so we turn to the black holes sorted by weight, beginning with the ones born from the deaths of stars, and moving outward across a range so wide it is difficult to hold in the mind. For now, let the shared shape of these objects settle. A boundary, a swirl, a ring of light, and a center we cannot yet see. That much is the same everywhere. The most familiar black holes are the ones that begin as stars. They are the natural end of a certain kind of life, the quiet remainder left when a massive star has spent everything it has. To understand them is to understand how the universe turns light into darkness, slowly and without malice, as a matter of simple accounting. A star is a long argument between two forces. Gravity pulls its enormous mass inward, always trying to collapse it toward the center. Against this, the star burns, and the heat of that burning pushes outward, holding the star up. For most of a star's life, these two are in near-perfect balance. The star shines steadily, neither collapsing nor flying apart, because the outward push of its fire exactly answers the inward pull of its weight. This balance can last for millions or billions of years, depending on how much fuel the star has and how quickly it spends it. But no star burns forever. The fuel at its core is finite, and when it begins to run low, the balance starts to fail. In the most massive stars, the ones many times heavier than our Sun, the ending is swift and severe. The core, no longer able to hold itself up, gives way. In a fraction of a second, it collapses inward, falling toward its own center faster than the mind can follow. The outer layers of the star, left all at once without support, come crashing down and rebound in a titanic explosion, a supernova that can briefly outshine an entire galaxy. That explosion is the visible part of the story, the part that lights up the sky. But the quieter and stranger part happens at the center, in the collapsing core. If that core is heavy enough, nothing in nature can stop its fall. Not the pressure of packed particles, not any force we know, can hold against the weight. The core keeps collapsing, past the density of an atom, past every limit, until it closes a horizon around itself and disappears from the outside universe. Where a star once burned, there is now a black hole. These are the stellar mass black holes, and they carry a mass somewhere between a few times that of our Sun and a few dozen times. Despite holding the mass of several suns, they are astonishingly small. The horizon of such a black hole might be only a few kilometers to a few tens of kilometers across, so that the entire object, the remains of a star far larger than our own, could rest within the span of a single city. All that mass folded down into a darkness you could nearly walk across. They are also, by sheer count, the most common black holes in existence. A single large galaxy is thought to hold somewhere between tens of millions and hundreds of millions of them, scattered through its disk and halo, the accumulated remains of generations of dead stars. The overwhelming majority of these are entirely dark. They drift alone, with nothing falling into them, giving off no light of their own, and so they pass unseen. We know they must be there, but most will never be counted. For a long time, black holes of this kind were treated as little more than a curiosity of the equations, a strange possibility that nature might not actually bother to make. It seemed almost too extreme to be real, a place where matter simply vanished from the visible universe. Only gradually, as the glowing signatures of matter falling toward unseen heavy companions were found and measured, did it become clear that these objects are not merely allowed by the mathematics, but common throughout the cosmos. What began as a doubtful curiosity became one of the best established facts in astronomy, that stars really do collapse into black holes, and that the sky is quietly full of them. The ones we do find usually betray themselves through a companion. Many stellar mass black holes were born in pairs, alongside another star that has not yet died. When the two orbit closely enough, the black hole can pull streams of gas from the surface of its living partner. That gas does not fall straight in. It spirals into an accretion disk, heating as it goes, until it glows fiercely in a kind of light our eyes cannot see but our instruments can. This glow is how many of the first known black holes were discovered, not by seeing them, but by seeing the last bright cry of the matter falling toward them. Only certain stars are destined to become black holes, and they live fast and die young. A star, many times the mass of our Sun, burns through its enormous fuel supply at a furious rate, shining far more brightly than smaller stars, but lasting only a small fraction as long. Where a modest star like our own can shine steadily for many billions of years, a truly massive one may run its whole course in just a few million, a brief and brilliant life ending in collapse. The black holes born from stars are therefore the offspring of the rarest and most short-lived suns, the ones that blazed hardest and gave out soonest. The details of how a massive star ends and whether it leaves a black hole at all depend on more than its mass alone. The makeup of the star matters, in particular how much of it consists of elements heavier than the simple gases it was born from. Stars richer in these heavier elements shed more of their material to space through strong winds as they age, arriving at their deaths lighter than they began, and so more likely to leave a smaller remnant. Stars made of purer, simpler material hold onto more of their mass and can collapse more completely. The same starting weight can lead to different endings depending on what the star is made of and how much it has lost along the way. There appears to be a lower limit to how small a star-born black hole can be. Below a mass of roughly 2 to 3 times that of our Sun, the collapsing core does not become a black hole at all. Instead, it stops at an earlier stage, as a neutron star, an object almost as extreme, packed to the density of an atomic nucleus, but still holding itself up, just barely, against the final fall. Only when the core is heavier than this threshold does gravity win completely and the horizon close. There is, in this sense, a smallest possible weight for a black hole born from a star. There is also a curious gap higher up the scale, a range of masses that single stars seem unable to produce directly. In the most massive stars of all, the conditions at the core can become so extreme that the entire star is torn apart in a single runaway explosion, scattering all of its matter and leaving nothing behind. No core survives to collapse, and so no black hole forms. Above this range, at even greater masses, the star may collapse directly with little or no explosion. The result is a gap in the middle, a span of masses that the ordinary death of a star tends to skip over. The ripples in space from merging black holes have taught us that these star-born objects come in a wider range of sizes than once expected. Before such ripples could be detected, the black holes known from their glowing companions clustered around a fairly modest range of masses. But the mergers revealed heavier ones, black holes noticeably more massive than the familiar examples, formed from stars that must have held onto more of their mass than expected, or built up through earlier unions. Each detected merger adds another entry to the tally, slowly filling in the true spread of star-born black hole masses and reminding us how much was hidden while we could only see the ones that happened to shine. There is a strange finality to what a black hole does with the star that made it. Everything that gave the star its identity, its particular blend of elements, the patterns of its light, the long story of its burning, all of it is drawn inward and sealed away, reduced from the outside to those same few plain numbers. The black hole remembers nothing of the star in any way we can read. A sun that shone for millions of years, that may have warmed worlds of its own, leaves behind an object that carries no trace of that history on its surface, only its weight and its spin. It is a kind of forgetting written into the laws of nature, gentle and complete. Once formed, a stellar mass black hole is a remarkably stable thing. It does not burn, so it cannot run out of fuel. It does not cool in any way that matters over the life of a galaxy. Left alone, it simply persists, a small permanent fold in space where a star used to be. It may wander for billions of years, occasionally passing near gas or stars, occasionally revealing itself, but mostly keeping its silence in the dark between the stars. The way we measure the mass of these hidden objects is itself worth understanding, because it reveals how something invisible can be weighed. When a black hole draws gas from a companion star, that companion still shines, and its motion can be tracked. A star bound to a heavy, unseen partner is swung along a wide, swift orbit, and the speed and size of that orbit reveal the mass of whatever holds it. In this way, without ever seeing the black hole, its weight can be read from the dance of the star beside it. The unseen is measured through its effect on the seen, a method that runs through the whole study of these objects. Not all star-born black holes announce themselves through a companion, and some of the most interesting are entirely alone. A black hole drifting through space by itself, with no star to feed on, gives almost no direct sign of its presence. But even these can occasionally be caught when one happens to pass in front of a more distant star. The black hole's gravity bends and briefly brightens the light of that background star, a passing flicker that betrays an unseen mass gliding by. Through such fleeting alignments, isolated black holes have begun to be found, drifting quietly and alone through the dark between the stars. The moment of a black hole's birth is not always gentle, and it can leave a lasting mark on the object's later life. The collapse and explosion that create a stellar black hole are rarely perfectly symmetric. A slightly lopsided explosion can give the newborn black hole a powerful push, a natal kick, sending it speeding away from its birthplace. Some black holes are launched fast enough to escape the very region where they formed, beginning their existence already in motion, wanderers from the first instant. The violence of the death that made them echoes on in the speed at which they travel. There is also a deep connection between these collapses and some of the brightest flashes in the universe. When certain very massive, rapidly spinning stars collapse to form black holes, the process can channel enormous energy along the poles, producing brief, tremendous beams of radiation that briefly outshine everything around them. These flashes can be seen across almost the entire observable universe, a signal of a black hole coming into being in a distant galaxy. In this sense, some black holes announce their own birth with one of the most powerful signals nature produces, a final cry of light before the long silence that follows. It is worth pausing on what these objects really are. Each stellar mass black hole is the fossil of a sun. It marks a place where a great burning sphere, larger and brighter than our own star, lived out its life and then folded itself away. The light that star gave off over millions of years has long since traveled outward into the universe, and what remains behind is only the weight drawn down into a point we cannot see. There is something almost peaceful in it. The violence of the collapse is long over. What is left is quiet and small and enduring. These star-born black holes are the foundation of the whole family, the most numerous and the most straightforward. But they are far from the largest. To find the giants, we have to leave the graveyards of individual stars and travel to the centers of galaxies, where black holes of a wholly different scale hold court. Between the star-born black holes and those giants lies a class that was, for a long time, strangely missing. And so we move gently upward, out of the range of dying stars, toward the great dark hearts of galaxies and the elusive objects that bridge the two. Having met the black holes born from single stars, we now climb the scale of mass, and as we climb, the objects grow rarer and stranger. The next step up was, for a long time, the hardest to find. A whole class of black holes suspected, but not seen, sitting in the gap between the star-born objects and the giants at the centers of galaxies. These are the intermediate mass black holes, and their story is one of patient searching for something that theory insisted should be there. An intermediate mass black hole carries somewhere between about 100 and 100,000 times the mass of our Sun. This is far too heavy to have come from the collapse of any single star, yet far too light to be one of the great galactic anchors. For a long time, this middle range was nearly empty in the records, a puzzling absence. There were the small black holes, well understood, and the enormous ones, plainly visible at galactic centers, but the bridge between them seemed to be missing. It was called, fittingly, the missing link of the black hole family. The difficulty was not that they were rare so much as that they were quiet. An intermediate black hole is not small and bright in the way a feeding stellar mass black hole can be, and it is not surrounded by the brilliant, unmistakable activity of a galactic giant. It occupies an awkward middle ground, large enough to be hard to make and small enough to be easy to overlook. Finding them meant looking in the right places, and the right places turned out to be the dense hearts of great star clusters and the centers of small galaxies. Slowly, the evidence has accumulated. In certain crowded clusters of stars, the motions of the stars near the center hint at an unseen mass, holding them in tighter orbits than they should otherwise keep. In some small galaxies, faint signs of a central black hole appear at a mass squarely in the intermediate range. And most tellingly, the ripples in space released when two black holes collide have, in a few cases, produced a merged object of just this size, caught in the very act of forming. The middle class, it seems, is real after all. How do such black holes come to be? There are several possible paths, and they may all occur. In a dense star cluster, black holes and heavy stars sink toward the center over time, and there they can merge again and again, each collision building a slightly larger object, until a black hole of intermediate mass is assembled from many smaller ones. In the early universe, unusually massive stars may have collapsed to produce heavy black holes directly. And some intermediate black holes may simply be the seeds, the starting points from which the true giants would later grow. That last idea is why this middle class matters so much. If the enormous black holes at the centers of galaxies grew from smaller beginnings, then at some point in their long history, they must have passed through the intermediate range on their way up. To study an intermediate black hole today may be to glimpse a galactic giant in its youth, caught before it grew into its full and overwhelming size. The middle class is, in this sense, a window onto the childhood of the largest objects gravity has ever built. And it is to those largest objects that we now turn. At the center of nearly every large galaxy, including our own, sits a supermassive black hole. These giants carry from 100,000 to many billions of times the mass of our Sun. They are not the remains of a single star, nor even of a cluster of stars. They are structures of a different order, so massive that they help govern the motion of the innermost regions of their galaxies, anchoring the great slow wheel of stars around them. These giants are not the exception but the rule. Nearly every large galaxy examined closely turns out to hold a supermassive black hole at its center, so consistently that their presence seems to be a basic feature of how galaxies are built. A galaxy without one would be the oddity. This near-universal company suggests that the growth of galaxies and the growth of their central black holes are bound together in some fundamental way, two processes that unfold side by side across the long history of the universe, each shaping and limiting the other. For all their mass, these central black holes make up only a tiny fraction of the galaxies they anchor, often less than 1,000th of the mass of the surrounding stars. A supermassive black hole is, in a sense, a small and heavy seed at the center of an immense structure, holding a weight enormous in itself, yet slight against the whole. And most of them, most of the time, are quiet. The blazing quasars are the rare few caught feeding heavily. Far more common is the calm, dormant giant, like the one at our own galaxy's center, waiting in near silence, its great mass betrayed only by the motion of the stars that circle it. Our own galaxy holds one of these. At its center, hidden behind thick clouds of gas and dust, lies a black hole with the mass of about 4 million suns. As these giants go, it is modest and rather quiet, not feeding heavily, not blazing. We know it is there because we can watch the stars nearest the center racing along tight, swift orbits, circling something we cannot see, something small and dark and extraordinarily heavy. Only a black hole can explain their motion. It sits at the center of everything, calm for now, holding its place. The scale of the largest supermassive black holes is difficult to hold in the mind. The horizon of such an object can be wider than the entire orbit of the outer planets in a system like ours. If one were placed where our sun is, its darkness alone would swallow the whole familiar solar system and reach far beyond. And yet, because the mass is so vast and so spread out, the tidal stretching at its horizon is gentle. A traveler could cross that enormous boundary without being torn apart, drifting inward across a threshold larger than a planetary system, feeling nothing at all as the way back quietly closed. These giants are bound up with their galaxies in a way that still surprises those who study them. The mass of the central black hole is closely tied to the properties of the surrounding swarm of stars, as though the two grew up together, each shaping the other. A larger galaxy tends to hold a larger central black hole in a proportion so consistent that it cannot be coincidence. Somehow, over billions of years, the growth of the black hole and the growth of the galaxy stayed in step, though the black hole is a tiny fraction of the whole. The connection is real, and it is not yet fully explained. At the very top of the scale sit the largest known black holes of all, the ultramassive ones, weighing tens of billions of times the mass of our Sun. These are found at the centers of the most massive galaxies, often the great galaxies that sit at the hearts of enormous clusters. Their horizons stretch across distances, measured not in kilometers, but in light days, spans so wide that light itself takes days to cross them. They are the largest single structures that gravity has ever assembled, each one a dark keystone holding up a galaxy. Theory hints at the possibility of black holes larger still, a proposed class sometimes given the almost playful name of stupendously large black holes, which would reach beyond 100 billion times the mass of our Sun. Whether nature has actually made any is unknown. There seems to be a natural ceiling to ordinary growth, because beyond a certain size, the disk of matter feeding a black hole becomes unstable and can no longer supply it steadily. Any object above that ceiling, if it exists, would likely be a relic of unusual conditions long ago, rather than the product of steady feeding. For now, the stupendously large remain a question at the far edge of the scale. The influence of these giants reaches far beyond their horizons, out into the galaxies they anchor. When a supermassive black hole feeds and blazes, it pours energy into the gas around it, heating that gas and driving it outward in great winds. This can slow or even halt the forming of new stars across large regions of the galaxy, as the gas that would have made those stars is warmed and pushed away. In this way, a central black hole, tiny compared to the galaxy around it, can shape the destiny of the whole, deciding in part how many stars a galaxy will make and when its star-forming days will end. The connection between black hole and galaxy runs in both directions. There is a region around each of these giants where its gravity rules over everything else, called its sphere of influence. Within it, the black hole is the dominant power, governing the orbits of the stars and gas that stray near. Outside it, the combined gravity of the galaxy's own stars takes over. The size of this region depends on the black hole's mass, and by watching how stars move as they cross into it, astronomers can weigh the unseen giant at the center. It is the same method used for the star-born black holes, carried out on a vastly larger stage, reading the mass of the invisible from the motion of the visible. We have, in recent times, come remarkably close to seeing these giants directly, or rather, to seeing their shadows. By gathering the faint radio glow from the hot matter swirling around a nearby supermassive black hole and combining the view from instruments spread across the whole face of the Earth, it has become possible to capture an image of the dark silhouette of a horizon, ringed by the light of matter bent around it. The picture shows exactly what the equations long predicted, a round shadow surrounded by a bright, uneven ring. To look at such an image is to look at the edge of one of these giants, at the boundary itself, drawn against the glow of everything falling in. The very largest of these giants sit at the centers of enormous clusters of galaxies, in the single biggest galaxy of each such gathering. These central galaxies have grown by swallowing others over the ages, and their black holes have grown along with them, feeding and merging until they reached sizes beyond all others. Around some of them, the surrounding cluster gas shows signs of having been repeatedly heated and pushed outward by past outbursts, a record written in the gas of feeding seasons long finished. The giant may be quiet now, but the marks of its former activity linger for ages afterward, a fossil trace of the power it once poured out. There is a real sense in which these largest black holes may have finished their growing. Having consumed or driven away the gas within their reach, and having heated their surroundings enough to keep fresh gas from settling in, they can enter a long, quiet old age, neither growing nor fading, simply persisting at the centers of their vast galaxies. They become monuments to an earlier, more active time, holding more mass than anything else in the universe, yet doing very little now but turning slowly and keeping their stars in order. In them, the story of black hole growth reaches its calm and final chapter. The greatest puzzle these objects pose is one of time. When we look at the most distant reaches of the universe, we are also looking into its distant past, seeing light that set out long ago. And in that early era, when the universe was young, there were already fully grown giant black holes, blazing as quasars, holding the mass of billions of suns. This is difficult to explain, because there seems hardly to have been enough time for them to grow so large by ordinary feeding alone. How the giants assembled so quickly, so early, is one of the open questions that drives much of the study of these objects, and it points towards special paths of formation that we will come to later in this journey. So the range runs from a few suns to tens of billions, from the small dark remains of a star to the vast anchors of galaxies. It is one of the widest spans of scale anywhere in nature, and every point along it is the same simple condition, gravity closed over matter, differing only in how much. We have climbed, in this survey, from the starborn to the giants. Now we turn the other way, downward and inward, toward the smallest black holes of all, and toward objects so ancient they may have formed before the first star ever shone. Let the giants rest at the centers of their galaxies, turning slowly, holding their stars. We are going to the other end of the scale now, into the very small and the very old. We have traveled up the scale of mass to the great galactic giants. Now we go the other way, down past the starborn black holes and beyond, into a stranger territory. Here the black holes become small, in some cases almost unimaginably small, and here too they become old, reaching back toward the very beginning of the universe. These are the smallest and most ancient members of the family, and much about them lives on the boundary between the known and the theoretical. The ordinary way of making a black hole, the collapse of a star's core, has a smallest possible product, set by the point at which a neutron star gives way instead. But nature, at least in theory, may have had another way to make black holes, one that needed no stars at all, and that had no such lower limit. To find it, we have to go back to the first moments after the universe began, when everything was hot and dense and packed together far more tightly than anything today. In those first instants, matter and energy were not spread perfectly evenly. There were slight variations, regions a little denser and regions a little thinner, ripples in the newborn cosmos. Where the density was high enough, In some small patches, gravity could have taken hold at once, collapsing that concentration directly into a black hole without waiting for any star to form. These are the primordial black holes, born not from the death of a star, but from the raw unevenness of the early universe itself. Because they came from these early conditions, rather than from the collapse of stars, primordial black holes are not bound by the usual limits. They could, in principle, span an enormous range of masses. Some might be tiny, no heavier than a mountain compressed to the size of a particle. Others might be far larger, comparable to the black holes born from stars, or heavier still. Their possible variety is one of the reasons they are so interesting and so difficult to rule out. They could be almost any size, hiding almost anywhere. The mass of a primordial black hole would have been set by the moment of its birth. In the earliest instance, the region of the universe that could act together, that could collapse as a unit, was very small, and it grew larger as time passed. A black hole forming in the very first fraction of a second could therefore be tiny, while one forming a little later could be far more massive, because a larger region had come within reach of its own gravity. In this way, the age of the universe at the moment of collapse would fix the size of the black hole produced, so that primordial black holes of every scale might trace back to different instants of the beginning. Not every dense patch of the early universe would have collapsed, only those that were dense enough to overcome the fierce outward pressure of that hot, early time. This is why primordial black holes, if they formed at all, would have required just the right conditions, regions where the small ripples in density happened to be unusually strong. Whether such strong ripples existed in sufficient numbers depends on the precise character of the newborn universe, on details we are still working to understand. And so the very question of whether these ancient black holes exist reaches back to the deepest questions about how the universe began. No primordial black hole has ever been confirmed. They remain, for now, a possibility rather than a certainty. But they are among the most actively explored ideas in the study of black holes, and there is a particular reason for the interest. Much of the matter in the universe is invisible. It gives off no light and reveals itself only through its gravity, tugging on the stars and galaxies we can see. This unseen matter is one of the great open questions of astronomy, and primordial black holes offer a tempting possible answer. If primordial black holes formed in the right numbers and the right range of sizes, they could account for at least part of this hidden mass. They would be dark by nature, ancient, and scattered throughout every galaxy, unseen but not undetectable, pulling quietly on everything around them. Whether they actually make up a meaningful share of the missing mass is not known. The idea has been neither confirmed nor ruled out entirely, and it remains one of the more elegant possibilities on the table, a way to explain something vast using something very small and very old. There is a further role these ancient black holes might have played, one that connects the smallest and oldest to the very largest. If some primordial black holes formed heavy enough, they could have served as the seeds from which the giant black holes at galactic centers later grew. This would help resolve one of the puzzles we met earlier, the difficulty of explaining how such enormous black holes appeared so early in the history of the universe. Beginning already large, born directly from the early cosmos rather than from the slow collapse of stars, such seeds would have had a great head start, time enough to feed and grow into the giants we see even in the young universe. In this picture, the ancient and the vast are linked across the whole span of cosmic history. A black hole formed in the first fraction of a second, from nothing but the unevenness of the newborn universe, could be the distant ancestor of a galactic giant blazing as a quasar an age later. Whether this is truly how the giants began remains uncertain, one possibility among several. But it is a striking thought that the smallest and oldest members of the family might be the origin of the largest, and that the great dark anchors of galaxies might trace their lineage all the way back to the first instance of time. The smallest black holes of all, whether primordial or purely hypothetical, are strange in a way the large ones are not. When a black hole is small enough, the rules of the quantum world, which govern the behavior of the tiniest things, begin to dominate. Such an object is called a micro-black hole, and it would be a place where two great descriptions of nature, the physics of gravity and the physics of the very small, are forced to describe the same thing at once. This is precisely the meeting point our theories handle least well, and so micro-black holes are as much a puzzle as an object. A micro-black hole with the mass of a small mountain would have a horizon smaller than a single atom. All the weight of a mountain folded into a space finer than the smallest speck. And yet, remarkably, such an object would not simply sit there in the dark. It would glow. The smallest black holes are not perfectly black at all, and understanding why leads to one of the most beautiful and surprising ideas in all of physics, an idea that ties the fate of the tiniest black holes to the fate of the greatest, and that we will return to at the end of our journey. For now, it is enough to know the direction of it. A black hole slowly leaks energy through a subtle quantum process near its horizon, and in leaking energy, it loses mass. The smaller the black hole, the faster and hotter this leak becomes. A great black hole loses so little that it will effectively last forever by any measure that matters today. But a truly small one would glow brightly, shedding its mass, growing hotter as it shrank, until in a final flourish it would vanish entirely. The smallest black holes, then, are not permanent. They are fleeting by cosmic standards, bright and brief. This is why nothing in the present universe is known to make micro-black holes, and why they have never been observed. The conditions needed to compress so little matter so far do not arise anywhere we can see today. They belonged, if they existed at all, to the extreme early universe, or they live in the thought experiments of those who study the deepest laws of nature. As real objects, they are unconfirmed. As ideas, they are invaluable, because they force our two great theories to speak to each other. The way the smallest black holes fade deserves a closer look, because it turns the usual picture upside down. For almost everything in the universe, larger things last longer and hold more heat. But for black holes, it is the reverse. A large black hole is cold, so cold that its temperature lies just the faintest breath above the coldest possible, and it fades so slowly as to seem eternal. A small black hole is hot, and the smaller it grows, the hotter it becomes, and the faster it sheds its mass. This runaway quality means that the final stretch of a small black hole's life is not a gentle fading, but a quickening, a brightening rush toward the end. If such an object exists and reaches the last of its mass, it does not simply wink out quietly. It finishes in a final burst, releasing the remainder of its energy in a brief, brilliant flash. Nothing in the present universe is known to be doing this, and no such flash has been confirmed. But the possibility is one of the ways that primordial black holes, if they exist, might one day be detected. A tiny black hole formed in the early universe, reaching the end of its long, slow fade in the present era, would announce its passing with a final flourish of energy, a distant signal of an ancient object, at last completing its life. The masses in which primordial black holes might exist are constrained from many directions, and this is part of why the idea is studied so carefully. If they were too plentiful in certain size ranges, they would bend the light of background stars too often, or disturb the motions of stars and gas in ways we would already have noticed, or leave marks on the light left over from the early universe. Each of these effects rules out some possibilities and leaves others open. What remains are certain windows of mass in which primordial black holes could still be hiding in large numbers, quietly making up part of the universe's unseen weight without betraying themselves. There is something almost fitting in the idea that the smallest and oldest black holes might be the ones that solve the largest mystery. The unseen matter that outweighs everything we can see, that shapes the growth of galaxies and holds them together, remains unidentified. That it might turn out to be a scattering of ancient black holes, formed in the universe's first instance and drifting dark ever since, would tie the very beginning of time to the structure of everything that came after. Whether or not this proves true, it is a reminder that the smallest objects in this survey may carry some of its heaviest questions. It is worth holding, for a moment, the sheer sweep of what these smallest objects represent. A single one, no larger than a grain and yet as heavy as a mountain, would carry within its tiny boundary the same essential nature as the giant anchoring a galaxy. The rules that govern it are the same rules, only pressed to their limit, where the world of the very small and the world of gravity are forced into a single description. In studying these least of black holes, we are really studying the seam where our understanding of nature must one day be sewn together. There is a quiet wonder in this end of the scale. At the top sat black holes wider than solar systems, anchoring whole galaxies. Here at the bottom are objects that may be smaller than atoms, that may predate the first stars, that may be drifting unseen through the space around us this very night, holding the mass of mountains in spaces we could never see. The same condition, gravity closed over matter, but drawn so small and so old that it brushes against the beginning of time itself. We have now seen black holes sorted by their weight, from the smallest possible grains to the largest structures ever built. But mass is only the first of the three numbers that define these objects. The other two, spin and charge, give rise to a different way of sorting them, not by how heavy they are, but by the exact shape the mathematics takes. There are only a handful of these shapes, a small and complete set of exact descriptions, and together they reveal what a black hole most deeply is. And so, from the very small and the very old, we turn now to the pure forms drawn by the equations themselves. Let the smallest black holes drift for a while at the edge of thought. We are going to the mathematics now, where the family narrows to just 4 shapes. We leave behind for a while the question of how heavy a black hole is and ask a different one. What are the possible shapes a black hole can take in the pure language of the equations that describe them? The answer is one of the most satisfying facts in all of physics. There are only 4. Out of all the complexity of the universe, an isolated black hole can be fully described by just 4 exact solutions, distinguished only by whether it spins and whether it carries charge. Everything else is detail. This narrowness follows from the plainness we met earlier, the idea that a black hole has no hair, that it can be captured in only 3 numbers: mass, spin, and charge. Since mass is always present, the shapes are sorted by the other 2. A black hole either spins or it does not, and it either carries charge or it does not. 2 choices, 2 ways each, and so 4 possible forms. It is a rare thing in nature, a family of objects so complete that it can be laid out on the fingers of one hand. The first and simplest shape has mass, and nothing more. It does not spin, and it carries no charge. This is the plainest black hole there can be, perfectly round, with a single horizon and a single point at its center, where the equations reach their limit. It was the first exact description of a black hole ever found, worked out from the equations of gravity not long after they were written down. Everything about it is set by its mass alone. Give it a mass, and the entire object follows, its size, its horizon, its shape, all determined by that one number. This simplest form is the one drawn in most explanations, the clean picture of a round darkness surrounding a central point. And yet, for all its usefulness, no real black hole is expected to be exactly like this. The reason is motion. Everything in the universe turns. Stars spin, clouds of gas swirl, and anything that collapses carries that turning inward with it. A black hole formed from something that spun will itself spin. And so the perfectly still black hole, elegant as it is chiefly a teaching tool, the baseline against which the more realistic shapes are measured. There is a hidden depth to this simplest solution that took time to appreciate. It turns out that the region outside any round, non-spinning mass looks exactly the same, whether that mass is a black hole, a star, or a planet of the same weight. The outside space cannot tell the difference. This means that if our own sun were somehow crushed into a black hole without losing any mass, the orbits of the planets would not change at all. The Earth would continue in its familiar path, colder and darker, but held by exactly the same gravity as before. A black hole is not a cosmic vacuum that reaches out to pull things in from afar. Its gravity, at a distance, is no different from that of any other object of the same mass. What makes a black hole different is not the strength of its pull at a distance, but how close you can come to it. Because all its mass is drawn down into so small a space, you can approach far nearer to the center than you ever could with a star, and it is only there, close in, where the ordinary object's surface would have been, that gravity climbs to its extreme. The danger of a black hole lies not in some special reaching power, but in the room it makes for you to fall, the way it clears the space around its center, so that nothing stops the descent until the horizon itself. The second shape adds charge but still no spin. Give the black hole an electric charge, and its structure changes in a subtle and revealing way. Instead of a single horizon, there can now be two, an outer and an inner one, nested inside each other like shells. Between these two horizons, the relationship between space and time behaves in ways that do not occur in the simplest case. It is a richer geometry, and it introduces an idea, the inner horizon, that will return in the more realistic shapes. But this charged, non-spinning form is, like the simplest one, mostly a creature of theory. Real black holes are not expected to hold any significant charge, and the reason is the universe around them. Space is filled with charged particles of both kinds, positive and negative. Any black hole that began to build up a charge would quickly attract the opposite kind and pull it in, neutralizing itself almost as fast as it charged. So while the charge solution teaches us a great deal about how a second property reshapes a black hole, nature is not thought to keep its black holes charged for long. The third shape is the one that matters most, because it is the one that actually exists. Give a black hole spin but no charge, and you have the form that describes real black holes throughout the universe. Since everything that collapses tends to rotate, and since black holes are not expected to hold charge, this spinning, uncharged shape is the working description for the genuine objects out there. When astronomers speak of an actual black hole at the center of a galaxy, this is the mathematics behind it. Spin changes a black hole in several striking ways. The central singularity is no longer a single point. It is stretched into a ring, turning in the plane of the black hole's rotation. There are two horizons again, an outer and an inner, as in the charged case. And around the outer horizon lies the ergosphere, that region of dragged space where nothing can hold still. From that swirling region, energy can be drawn out, and this is thought to be one of the ways black holes come to launch their tremendous jets, feeding on their own rotation to light up the space around them. A spinning black hole cannot turn at any speed it likes. There is a maximum rate set by its mass, beyond which it cannot spin. As it approaches that maximum, its structure changes, the two horizons drawing closer together. A black hole pushed all the way to that limit is given a special name, the extremal black hole, and it is a curious and important edge case that we will come to in a moment. For now, it is enough to know that spin, like everything about a black hole, has a ceiling it cannot exceed. The claim that only 3 numbers describe a black hole is a stronger statement than it may first appear, and it took real effort to establish. One might expect that a black hole formed from a lumpy, complicated collapse would carry some memory of that complexity, some bumps or ripples on its surface, some feature betraying what went in. But it turns out that any such irregularities are shed away almost immediately after a black hole forms, radiated off as ripples in space, until what remains is perfectly smooth, described entirely by its mass, its spin, and its charge. A black hole erases its own imperfections in the act of settling down. This is why the word hair is used. Hair would be any extra detail, any distinguishing feature beyond the 3 allowed numbers, and black holes are found to have none. 2 black holes with the same mass, spin, and charge are not merely similar but truly identical, interchangeable in every respect that can be measured from outside. Nowhere else in nature is such perfect simplicity found. A star, a planet, a grain of dust each carries endless detail. A black hole, the most extreme object of all, is also the plainest, stripped down to just 3 numbers and nothing more. The 4th and final shape holds all 3 properties at once: mass, spin, and charge, together in a single object. This most general form contains all the others within it. Remove its charge, and it becomes the spinning shape. Remove its spin, and it becomes the charged shape. Remove both, and it collapses to the simplest form of all. In this sense, it is the parent of the whole family, the fullest expression of the idea that 3 numbers are all a black hole needs. Like the spinning and charged cases, it has an inner and an outer horizon, and from its rotation, a ring at its center and an ergosphere around it. This most general shape, complete as it is, remains mostly a matter of theory, precisely because real black holes are not expected to carry charge. But it completes the picture. It shows that with just those 3 numbers, mass and spin and charge, every possible isolated black hole is accounted for. There is nothing else to add. The universe, in this one corner, has been fully mapped, and the map has only 4 regions. That brings us to the strange limiting case mentioned a moment ago. An extremal black hole is one pushed to the very edge of what it can be, spinning as fast as it possibly can, or carrying the most charge it possibly can for its mass. At this limit, the inner and outer horizons merge into a single surface, and something remarkable happens to the object's character. In the quantum description, its temperature falls towards 0, so that it becomes, in a sense, as cold as a black hole can be. True extremal black holes are probably never quite reached in nature, because the closer an object comes to the limit, the harder it becomes to add the last increments of spin or charge. But as an idea, the extremal case is precious. It serves as a clean and simple laboratory in which the deepest questions about black holes and the quantum world can be studied. The dragging of space by a spinning black hole is worth lingering on, because it is one of the most counterintuitive effects in all of nature. Around a rotating black hole, space is not a still stage on which things move. It is itself set turning, carried around in the direction of the spin like water circling a drain. Within the ergosphere, this dragging is so complete that no object, however powerful, could hold still against it. To remain in one place would require moving faster than light in the opposite direction, which nothing can do. And so everything within that region is swept along, not by any force pushing on it, but by the turning of space itself. From this swirling region, energy can actually be drawn out, and this is one of the deepest reasons spinning black holes matter. It is possible, in principle, for an object entering the ergosphere to leave again, carrying more energy than it brought in, energy stolen from the black hole's rotation. Each such theft slows the black hole's spin by the smallest amount. On the grand scale, it is thought that processes like this, tapping the enormous rotational energy stored in a spinning black hole, help drive the tremendous jets that active black holes launch across thousands of light years. The spin is not idle. It is a reservoir of power, and nature has found ways to spend it. Spin also decides how closely matter can orbit before it must fall in. Around every black hole, there is a closest stable orbit, an innermost ring inside which no steady circling is possible, and everything must spiral inward to the horizon. For a still black hole, this innermost orbit lies well outside the horizon. For a rapidly spinning one, in the direction of the spin, it lies much closer in. This matters greatly, because the closer matter can orbit before falling, the more energy it can release on the way down. A rapidly spinning black hole is therefore a more efficient engine, wringing more light from the matter it consumes than a still one ever could. By reading the light from the innermost edge of an accretion disk, astronomers can even estimate how fast a real black hole is turning. The inner edge of the disk sits at that closest stable orbit, and its location depends on the spin. So the glow of matter making its final circles carries, encoded within it, a measure of the black hole's rotation. In this way, the abstract third number of the mathematics, the spin, becomes something that can actually be gauged for real objects out in the universe, read from the light of matter in its last moments before the fall. So the mathematics gives us 4 shapes and one important edge: a still black hole, a charged one, a spinning one, and one with both charge and spin, along with the extremal limit at the far edge of possibility. Of these, only the spinning shape describes the real objects out in the universe, but all of them together reveal what a black hole most deeply is, an object of astonishing simplicity, fully captured by 3 numbers. Having seen what black holes are, in mass and in mathematics, we can now ask what they do. For the same black hole can wear very different faces depending on whether it is feeding or resting, and it is to those changing faces that we turn next. Let the 4 shapes settle quietly into place. We are moving now from what a black hole is to how it behaves, from the still equations to the living sky. A black hole, by itself, gives off no light. And yet, some black holes are among the brightest objects in the entire universe, while others are so dark they can hardly be found at all. The difference is not in the black hole. It is in what surrounds it, and in whether it is feeding or at rest. The same object, with the same mass and the same spin, can blaze like a beacon across the cosmos, or sleep in near total silence. In this way, black holes are sorted not by what they are, but by what they are doing. When a black hole has a rich supply of matter falling toward it, it becomes one of the most luminous things there is. The matter does not fall straight in. It spirals inward through an accretion disk, and as it spirals, it is compressed and heated to temperatures beyond imagining, until it pours out light across every kind of radiation. A supermassive black hole feeding in this way turns the center of its galaxy into a brilliant core, an active heart shining far brighter than all the stars around it. The black hole itself stays dark and unseen, but the matter in its grip announces its presence to the whole universe. The brightest of these feeding giants are called quasars, and they are difficult to overstate. A quasar is a supermassive black hole consuming matter at a furious pace, glowing so intensely that it can outshine every one of the hundreds of billions of stars in its host galaxy combined. From across almost the entire observable universe, a quasar can still be seen, a single point of light that is, in truth, the death throes of matter falling toward a giant black hole. They are beacons visible across distances that stagger the imagination, and each one marks a black hole in the midst of a great feast. Quasars were far more common long ago, in the young universe, than they are today. In those early times, galaxies were rich with gas, and their central black holes fed heavily and shone brilliantly. As the ages passed, and the available gas was consumed or settled into stars, the great feeding slowed, and many quasars faded into quiet. When we look at distant quasars, we are looking far back in time, at an era when the universe blazed with the light of feeding giants far more than it does in the calmer present. The same feeding black hole can appear in a strikingly different guise, depending on how it happens to be oriented toward us. Some of these active giants launch narrow jets of matter and energy from their poles, and when one of those jets points almost directly at us, we are looking straight down the barrel of the beam. Such an object is called a blazar, and it shows rapid, dramatic changes in brightness, flickering and flaring as the jet points our way. A blazar is not truly a different kind of object from a quasar. It is the same kind of feeding black hole, seen from a special angle. The idea that a single kind of object can wear so many faces is one of the quiet triumphs in the study of these giants. For a long time, the various bright centers of galaxies were given many different names, as though they were many different kinds of thing. Only gradually did it become clear that a great many of them are the same underlying object, a feeding supermassive black hole seen under different circumstances. Whether one appears as a brilliant point of light, or as a source of enormous radio-emitting lobes, or as a rapidly flickering beacon, depends largely on how much it is feeding, and from what angle we happen to view it. Much of this variety comes down to a ring of thick gas and dust that often surrounds a feeding black hole well outside the horizon. Seen from the side, this ring hides the brilliant central region behind it, and the black hole appears muffled, its light softened and reddened. Seen from above or below, the bright core is laid bare, and the object blazes openly. One black hole, one act of feeding, but two very different appearances, depending only on our line of sight. Recognizing this has allowed a whole zoo of seemingly separate objects to be understood as variations on a single theme, the same engine turned to face us in different ways. There is a smaller version of all this drama, played out around the star-born black holes. When a stellar mass black hole in a binary system pulls gas from its companion star, it too can form a hot disk and launch its own miniature jets. Such an object is called a microquasar, a scaled-down echo of the galactic giants. It works in the same way, a disk of infalling matter and a pair of jets, but at a far smaller scale and on far faster timescales. Because everything happens more quickly around these smaller black holes, they offer a valuable chance to watch, in a human span of time, processes that take ages around the giants. The unifying lesson in all of this is that active black holes of every size work in fundamentally the same way. a disk of matter spiraling inward, heated to brilliance, sometimes paired with jets streaming from the poles. The differences between a quasar, a blazar, and a microquasar are largely differences of scale and viewing angle, not of underlying nature. It is the same machine, built at different sizes and seen from different directions, turning the fall of matter into some of the most powerful light in the universe. Between the blazing quasars and the silent sleepers lies a whole range of black holes, feeding gently at a slow and modest pace. Not every active black hole is a brilliant beacon. Many take in only a thin trickle of gas, glowing faintly at their centers, neither dark nor dazzling. The center of our own galaxy is one of these quiet feeders, taking in only the smallest amount of material and shining very dimly for its size. Across the universe, most active black holes are of this gentle kind, feeding slowly and glowing softly, the fierce quasars being only the rare extreme of a broad and mostly modest spectrum. Even the quietest black holes can stir from time to time. Our own galaxy's central giant, calm as it is today, shows faint signs of having been more active in the past, echoes of old outbursts written in the gas around it. A clump of matter drifting too close, a small cloud pulled inward, can briefly raise the black hole's glow before it settles back into quiet. These small stirrings are like the shifting of a sleeper who does not quite wake, reminders that even a dormant giant is not truly inert, only waiting, its long rest broken now and then by a passing meal too small to fully rouse it. But feeding is the exception, not the rule. Most black holes, most of the time, are not feeding at all. With little or no matter falling in, they produce almost no light, and they become extraordinarily difficult to detect. These are the dormant black holes, and they are almost certainly the most common state of all. The bright, active ones we can see across the universe are the rare few caught in a temporary season of plenty. The vast majority are sleeping, dark and quiet, giving away nothing. Our own galaxy's central black hole is one of these sleeping giants. It is not feeding heavily, and so it does not blaze. We know it is there only because we can watch the stars nearest to it moving along swift, tight orbits, circling a mass we cannot see. This is how the quietest black holes are found, not by their light, which is absent, but by their gravity, by the way they move the stars around them, and by the way they bend the light of more distant objects passing behind them. A dormant black hole hides in plain sight, betrayed only by its pull. A sleeping black hole is not sleeping forever. It can wake. If a fresh supply of gas drifts inward, or if an unlucky star wanders too close, the black hole can begin to feed once more, flaring back to life. One of the most dramatic ways this happens is when a star strays near enough to be torn apart by the black hole's tides. The star is stretched and shredded, part of it flung away and part of it pulled inward, where it briefly forms a hot disk that flares for months or even years before fading back to darkness. These events, in which a sleeping black hole is briefly stirred by the destruction of a passing star, light up giants that would otherwise be invisible. They offer a rare and fleeting glimpse of a black hole that spends nearly all its time in silence. They are less a type of black hole than a type of event, a moment of brightness in a long, quiet life, a sleeping giant that stirs, feeds once, and returns to rest. Through them, we catch sight of black holes we could never otherwise have found. There appears to be a natural limit to how brightly a black hole can steadily feed, and it comes from the very light it produces. As matter falls in and blazes, the outward pressure of that light pushes back against the gas still trying to fall. Feed too quickly, and the black hole's own brilliance begins to blow away its supply, choking off the flow. This sets a kind of ceiling on steady brightness, a balance between the pull of gravity drawing matter in and the push of light driving it away. The brightest quasars feed near this limit, glowing about as fiercely as their mass will allow, held in a delicate balance between hunger and glare. The jets that some active black holes launch are among the largest single structures in the universe. Streaming from the poles at nearly the speed of light, they can travel outward for hundreds of thousands of light years, far beyond the edge of the host galaxy, before finally slowing and spreading into vast, billowing lobes of glowing gas. A single such structure can dwarf the galaxy that produced it. These jets carry energy across enormous distances, heating the space between galaxies and stirring the gas of whole clusters. From a region no larger than a solar system, at the very center, comes an outflow that reshapes surroundings measured in millions of light years. The feeding of a black hole is not steady over the ages, but comes and goes in seasons. A giant may blaze as a quasar for a time, exhaust the gas within its reach, and then fall quiet, sleeping until a fresh supply arrives. Over the long life of a galaxy, its central black hole may wake and sleep many times, flaring and fading as gas flows inward or is used up. What we see when we look at any one black hole is only a single moment in this long cycle, a snapshot that cannot tell us, by itself, whether we have caught the object in a rare bright season or in one of its many long rests. The speed at which a black hole's brightness flickers carries a hidden message about its size. A source of light can only brighten or dim as quickly as light can cross it, so a rapidly flickering object must be small, while a slowly varying one may be large. By timing how quickly the light from an active black hole changes, astronomers can gauge how compact the glowing region must be and confirm that all that brilliance truly does come from a region no larger than a planetary system. The flickering of the light becomes a ruler, measuring the smallness of the engine at the center of all that brightness. So the sky holds both kinds, the blazing and the sleeping, and they are often the very same objects at different moments in their long lives. A quasar in the young universe may be a quiet giant today. A dark and silent black hole may flare to brilliance when a star drifts too near. The face a black hole shows us depends entirely on its circumstances, on whether there is matter to feed it, and on how we happen to be looking. Having seen the black holes that shine and the ones that sleep, we turn now to those that travel and those that pair, the black holes in motion and in company, and the several roads by which all of them are born. Let the bright ones and the quiet ones drift together in the mind for a moment. We are moving now to the black holes that are not alone. Black holes are not always solitary, and they are not always still. Some move in pairs, locked in a slow dance that can last billions of years and end in a single shattering union. Some travel alone, cast out from where they formed, drifting through the dark as silent wanderers. And all of them, whatever their fate, came into being along one of a small number of paths. In this part, we follow the black holes that pair and the ones that wander, and then trace the several ways every black hole is born. Many black holes begin their existence with a companion, because many stars are born in pairs. When two massive stars live and die together, they can leave behind two black holes bound by gravity, orbiting a common center. This is a binary black hole, and it is one of the most consequential arrangements in the universe. For a long time, the two may circle each other quietly, two dark objects turning in the space where two stars once burned, giving little sign of their presence. But such a pair is not truly stable over the longest spans of time. As the two black holes orbit, they stir the fabric of space itself, sending out faint ripples that carry energy away. Losing energy, the two draw slowly closer, their orbit tightening over millions and billions of years. The closer they come, the faster they circle. And the faster they circle, the more strongly they ripple space. And so the process quickens. What began as a slow, distant dance becomes, in its final moments, a furious inward rush. In the last instant, the two horizons meet and merge. Two black holes become one, larger than either alone, and the merger releases a burst of energy in the form of ripples through space, a brief tremor in the very geometry of the universe. These ripples spread outward at the speed of light, and they can be detected across billions of light years, a passing shiver in space that tells of two black holes becoming one. It is one of the few ways the universe lets us witness a black hole event directly, not by light, but by the trembling of space itself. There is a subtle and beautiful detail in these mergers. The black hole that results is slightly less massive than the sum of the two that formed it. Some small fraction of the total mass is not kept at all. It is carried away in that final instant as pure energy, as the ripples in space themselves. For a moment, during the merger, the power radiated in these ripples can exceed the combined light of every star in the observable universe, though it is carried not in light, but in the flexing of space. Then it is over, and a single, slightly lighter black hole turns quietly where two once danced. Mergers are also one of the ways black holes climb the ladder of mass. Each union builds a larger object from smaller ones, and in crowded environments, this can happen again and again. A black hole may merge, then merge once more, growing step by step. This is part of how the great black holes at galactic centers are thought to have assembled, not all at once, but through a long history of unions and feeding, each collision adding to the total over spans of time that dwarf the age of stars. Galaxy collisions, though they sound violent, unfold with a strange gentleness over spans of time beyond imagining. When two galaxies meet, their individual stars almost never strike one another, for the distances between stars are so vast that the two great swarms simply pass through each other, drawn and reshaped by their mutual gravity. Over hundreds of millions of years, the two galaxies weave together, throwing out long streamers of stars before finally settling into a single larger galaxy. It is not a crash so much as a slow merging, a coming together too gradual for any eye to follow, playing out across more time than stars themselves take to live and die. Our own galaxy is bound for such a meeting. A great neighboring spiral is drifting slowly toward us across the gulf between galaxies, and in a distant future, long from now, the two will begin their long embrace. The night sky of that far era would show the approaching galaxy growing ever larger, until the two at last flow together into one. And at the center of that combined galaxy, the two supermassive black holes, one from each, would sink toward a common center, there to circle each other and, in time, to merge. Even our quiet giant has a distant appointment of this kind, written far ahead in the slow motions of the cosmos. The largest pairs of all form when whole galaxies collide. Each large galaxy carries a supermassive black hole at its center, and when two galaxies merge, their two central giants sink slowly toward the center of the combined galaxy. There they may settle into a binary of their own, two supermassive black holes orbiting each other, destined over enormous stretches of time to spiral together and merge. Such giant unions are expected to send out the longest and deepest ripples in space of all, slow waves that stretch across the universe. Black holes can also be brought together without ever having been born as a pair. In the dense hearts of great star clusters, where stars and black holes are packed far more tightly than in ordinary space, chance encounters become common. Heavier objects tend to sink toward the center over time, gathering the black holes into the crowded core, where they meet, pair off, and are traded between partners in a slow gravitational dance. Two black holes that formed in different stars, even in different eras, can in this way find each other and settle into a binary, destined eventually to merge. This crowding allows black holes to climb the ladder of mass step by step. A black hole that forms a pair, merges, and then finds another partner can grow through successive unions, each one adding to its weight. In the densest clusters, this process may build black holes heavier than any single star could ever produce, carrying them up into the elusive middle range between the star-born objects and the galactic giants. The intermediate mass black holes we searched for earlier may owe their existence, in part, to exactly this patient assembly in the crowded cores of clusters, one merger at a time. Not every black hole stays where it was born. The very process of merging can give a newly formed black hole a powerful push. When two black holes unite, the ripples they send out are not always perfectly balanced, and the imbalance can act like a recoil, kicking the merged black hole in one direction. If the kick is strong enough, the black hole can be flung out of the dense region where it formed, sent drifting off on its own. Interactions between several black holes in a crowded cluster can eject one entirely as well. The result is a rogue black hole, a wandering, solitary object moving through space, bound to no companion and anchored to no center. Such a black hole gives almost no sign of itself. It does not feed, it emits no light, and it drifts silently through the dark. Only rarely does one betray its presence, when it happens to pass in front of a more distant star and bends that star's light for a moment, revealing an unseen mass gliding by. The space of a galaxy may be threaded with these quiet travelers, most of them forever unseen, dark wanderers among the stars. Having followed the black holes that pair and the ones that wander, we can gather together the ways they all come to be, the roads by which the entire family is born. There are several, and between them they explain why black holes span such an enormous range of sizes. The same end state, a horizon closed over collapsed matter, can be reached in more than one way, and each way tends to produce black holes of a particular scale. The most familiar road is the collapse of a massive star's core, the path we followed earlier, which gives rise to the star-born black holes. When a heavy star exhausts its fuel, its core falls inward and folds past its horizon, leaving a black hole of a few to a few dozen times the mass of our Sun. This road is traveled constantly across the universe, wherever massive stars reach the ends of their lives, and it is the source of the most numerous members of the family. A second road appears in the early universe, where some large clouds of gas may have collapsed directly into black holes without ever forming stars at all. Under the right conditions, an entire massive cloud could fall inward as a single unit, producing a heavy black hole seed in one step. This direct collapse is a leading explanation for a genuine puzzle: the question of how the giant black holes at galactic centers grew so large so early. Beginning life already thousands of times the mass of the Sun, such seeds would have had a great head start on their long growth. A third road is the slow building of giants, through repeated mergers and steady feeding, the path we traced through the binary black holes. A black hole that merges again and again and feeds on surrounding gas as it goes, can climb from modest beginnings to enormous size over billions of years. This gradual assembly links the whole family together, with the intermediate black holes serving as stepping stones between the star-born objects and the supermassive giants above them. It is a patient road, measured in the ages of galaxies. The detection of merging black holes through the ripples they send out is one of the quietest triumphs in the study of these objects. and it works in a way that is almost hard to believe. When two black holes merge, the ripples they release stretch and squeeze space itself as they pass, lengthening distances in one direction while shortening them in another by an amount almost impossibly small. To catch such a passing tremor, instruments measure the length of long paths with extraordinary precision, watching for the faint, rhythmic stretching that marks the arrival of a wave from a distant merger. When one passes, it leaves a rising tone, a chirp, as the two black holes spiral together faster and faster before they unite. That final union has its own distinct signature, a brief ringing as the newly merged black hole settles into its final shape. Just after two horizons become one, the resulting object is misshapen, and it quivers, shedding the last of its distortion in a fading tremor of ripples before it becomes a smooth, quiet black hole. This settling is called the ring down, and it carries information about the mass and spin of the object that has just formed. In it, we hear the newborn black hole announcing its size and its turning in the last notes of the event that made it. The kicks that mergers can deliver are worth returning to because they shape where black holes end up. The ripples released in a merger do not always leave evenly in all directions, and the imbalance acts like a recoil, pushing the merged black hole one way. Depending on how the two original black holes were spinning and how they came together, this push can be gentle or fierce. A strong enough kick can hurl the newly formed black hole clear out of its home galaxy, sending it off to wander intergalactic space alone. In this way, the very act of two black holes becoming one can cast the result into permanent exile. There is a stubborn puzzle in the merging of the largest black holes, the supermassive pairs formed when galaxies collide. Such a pair can spiral inward readily at first, but as they draw closer, they can run short of ways to shed the last of their energy, and their inward progress may stall while they are still some distance apart. How these giant pairs cross that final gap and complete their merger is not fully understood, and it remains an active question. The slow, long ripples such mergers would release are being sought by watching for their subtle imprint on the timing of distant natural clocks scattered across the galaxy. And a fourth road needs no star and no cloud, only the unevenness of the newborn cosmos itself, the primordial path we met among the smallest and oldest black holes. Where the early universe was dense enough, in some small patches, black holes could have formed directly from the raw ripples of the beginning. These, if they exist, could be almost any size, and they remain among the most intriguing possibilities in the whole study. 4 roads, then, all leading to the same quiet condition: gravity closed over matter, drawn at every scale, from the smallest to the greatest. We have now seen how black holes are born, how they pair, and how they wander. What remains are the black holes that live, for now, only in the equations, and the long, slow story of how all of them will end. Let the wanderers and the pairs drift on in the dark a little longer. We are going, at last, to the black holes of theory, and to the far future of them all. We come now to the outer edges of the family, to the black holes and their close cousins that live, for the present, only in the equations. Some of these may one day be found. Some may never be more than possibilities. But they are genuine branches of the black hole family tree, drawn from the same mathematics that describes the real objects, and they show how much the idea of a black hole still holds in reserve. Beyond them lies the last part of our journey, the long, slow story of how every black hole will finally end. Every black hole we have described so far keeps its center hidden. The singularity, that place where our theories reach their limit, is always wrapped safely inside a horizon, sealed away from the outside universe. But the equations do not obviously forbid a different arrangement, a singularity with no horizon around it, exposed to the outside. Such a thing is called a naked singularity, and it is a genuinely unsettling possibility, because it would mean a place where physics breaks down, sitting open to the rest of the universe rather than safely hidden. Most of those who study these objects suspect that nature does not allow this. There seems to be a principle at work, informally called cosmic censorship, that wraps every singularity safely inside a horizon, keeping the breakdown of physics forever out of sight. But whether the universe truly forbids naked singularities, or merely makes them very difficult to form, has not been settled. It remains one of the open and quietly troubling questions at the edge of the theory, a possibility that has not been closed off. For now, every black hole we know keeps its center decently hidden. There is also the deeper question of what actually sits at that center. The prediction of an infinite density troubles many, because infinities in physics usually signal that a theory has been pushed past its limits. And so some have proposed black holes with no true singularity at all. In these pictures, quantum effects halt the collapse before an infinite density is ever reached, leaving instead a dense but finite core. Such objects are sometimes called regular black holes, and they are attempts to replace the troubling infinity with something physics can actually describe. A related idea imagines that at the very center, where the collapse would otherwise run to infinity, quantum pressure brings it to a halt, leaving an extraordinarily dense but finite core. Over spans of time almost beyond comprehension, such a core might even slowly rebound. These proposals remain speculative, ways of removing the infinity at the center of a black hole and putting in its place a real, if extreme, object. Whether nature works this way is unknown, but the impulse behind the idea is a healthy one, a refusal to accept an infinity as the final answer. From certain deep approaches to combining gravity with the quantum world comes a still more radical picture, one that changes the very nature of a black hole's interior. In this view, a black hole has no empty inside and no central singularity at all. Instead, the entire volume within the horizon is filled with a complex quantum structure, and the horizon is not a sharp edge over emptiness, but the fuzzy outer surface of that structure. In this picture, there is no hollow interior waiting to swallow things whole. There is, all the way through, a densely woven quantum object. If this picture is correct, it would resolve two puzzles at once. It would remove the singularity, replacing the troubling center with genuine structure. And it would offer a way out of one of the deepest problems in all of physics, the question of what happens to everything that falls into a black hole. That question deserves its own telling, because it is among the most profound that the study of black holes has ever raised, and it grows directly out of the slow way these objects fade. For black holes, as we glimpsed among the smallest of them, are not perfectly black. Through a subtle quantum process near the horizon, a black hole slowly gives off energy, and in giving off energy, it loses mass. This slow radiance is one of the most celebrated ideas in modern physics, because it ties the world of the very small to the world of the very large, and it means that black holes, for all their apparent permanence, are not truly eternal. Given enough time, a black hole will radiate itself away entirely. The rate of this fading depends sharply on size, and in a way that runs against intuition. The smaller a black hole, the faster and hotter it radiates. A tiny black hole would glow brightly and vanish quickly, while a great one fades so slowly that the timescales involved dwarf the present age of the universe many times over. A black hole with the mass of a star loses so little at present that it actually takes in more from its surroundings than it gives off, and so it still grows rather than shrinks. The great fading has not yet begun for the large black holes. The universe is still too warm for them to start. But the universe is cooling, slowly, over ages beyond ordinary reckoning. Far in the future, long after the last stars have burned out and gone dark, the great black holes will finally begin their long, faint fade. One by one, across spans of time so vast that every number fails to convey them, they will give up their mass to the dark, growing slowly smaller and, at the very end, hotter, until each one vanishes in a final quiet flourish. The largest will be the last to go, the final structures of a universe returning, at last, to stillness. In that far era, black holes will be among the last things left, and then even they will be gone. This slow disappearance raises the profound puzzle mentioned a moment ago. Everything that ever fell into a black hole carried information with it, the details of what it was, its arrangement, its history. The deepest laws of physics seem to insist that such information can never be truly destroyed. And yet, if a black hole slowly radiates away and finally vanishes entirely, what becomes of everything that fell in? Where does that information go? The tension between the permanence of information and the disappearance of the black hole is one of the most important unsolved problems in all of theoretical physics. Its resolution, when it comes, is expected to teach us something new and profound about the nature of space, of time, and of reality itself. It may be that the information is somehow carried out in the faint radiance as the black hole fades. It may be that the fuzzball picture, with its densely structured interior, holds the answer. It may be something no one has yet imagined. What is clear is that the humble black hole, so plain that 3 numbers describe it, sits at the very center of the deepest questions we know how to ask. The possible answers to the information puzzle are as strange as the puzzle itself, and each one asks us to give up some comfortable assumption. One possibility is that the information is not lost after all, but is somehow carried out gradually in the faint radiance as the black hole fades, subtly imprinted on the escaping energy in a way too delicate to read, but real nonetheless. If so, then nothing is truly destroyed, and the black hole is less a place of erasure than a place of extraordinarily thorough scrambling, from which everything eventually returns in unrecognizable form. Another line of thought suggests that all the information about what fell in is somehow encoded on the horizon itself, on that two-dimensional surface, as though the contents of the interior were written on its boundary. This startling idea that the full description of a volume of space might be captured on the surface enclosing it has grown into one of the most influential notions in modern physics, reaching far beyond black holes into the study of space and time themselves. It is a hint, many believe, that space and gravity may be woven from something deeper, some underlying web of information of which the horizon is only the most visible expression. Whichever answer proves correct, the mere fact that black holes force these questions upon us is a measure of their importance. An object so simple that 3 numbers describe, it turns out to sit at the crossroads of every fundamental theory we have: gravity and the quantum world and the nature of information, all meeting at its edge. In wrestling with what happens inside and at the surface of a black hole, physics is really wrestling with the seams of reality itself, the places where our separate descriptions of nature must somehow be joined. The humble black hole has become one of the great teachers, precisely because it refuses to let those descriptions stay apart. And there is one more cousin to mention before we let the family rest, an object drawn from the same equations that give us black holes. The full mathematics of an idealized black hole contains, tucked within it, a kind of bridge, a tunnel connecting to another region of space. This is the simplest form of what is called a wormhole. In the basic solution, this bridge is not something anything could actually cross. It pinches shut too quickly, and it does not describe a real black hole formed from collapsing matter. But it arises naturally from the equations, and it remains one of the most tantalizing ideas at the meeting place of black holes, space, and time. There is, too, a mirror image of the black hole hidden in the same mathematics, a region that nothing could ever enter, from which matter and light could only pour outward. It would be, in a sense, a black hole running backward in time. No such object has ever been seen, and it is far from clear that any could exist in reality. But it, like the wormhole bridge, emerges from the equations as a natural counterpart, a reminder that the mathematics of these objects is richer and stranger than the objects we have actually found. To understand the long future of black holes, it helps to imagine the great eras the universe will pass through. We live now in the age of stars, when galaxies shine and new suns are still being born. But this age will not last forever. In time, the gas that makes new stars will run low, and one by one the existing stars will burn out, until the last of them fades and the galaxies go dark. The universe will then enter a long, dim era, lit not by stars but by the faint glow of their cooling remains, and by the occasional flicker of black holes at their centers. In that far future, black holes will inherit the universe. Long after the stars are gone, they will remain, the last great structures standing, holding the mass of what were once galaxies. For an almost unimaginable span, this will be the age of black holes, an era in which these dark objects are the dominant features of a cooling, emptying cosmos. They will drift and occasionally merge, and around them the universe will grow ever colder and ever more still, until at last even the black holes begin their own slow fade. And fade they will, through that faint radiance we have spoken of. But the timescales defy every attempt to grasp them. If the present age of the universe were shrunk to a single heartbeat, the time it would take the largest black holes to evaporate would still stretch beyond any comparison the mind can hold. They will outlast the stars by a margin so vast that the entire history of the universe, so far, from its beginning to this very night, is less than the faintest first instant of their long decline. And yet, even for them, an ending waits. Nothing, it seems, is truly permanent, not even these. The very last black hole to evaporate will mark a kind of ending for the universe itself. When the greatest of them has finally given up the last of its mass in a final, quiet flourish, there will be nothing left of the grand structures that once filled the cosmos. What remains will be only a thin, cold haze of light and particles spread through a space grown unimaginably vast and empty. The universe will have returned, in the end, to a featureless quiet, the long stillness after everything has run its course. The black holes will have been the last to go, the final keepers of matter, before even they released it into the dark. There is a strange comfort to be found in this, rather than a sadness. The same slow processes that will one day carry the black holes away are the processes that made the stars, that built the galaxies, that gave rise to everything, including us, for a while, in the middle of it all. To know that even black holes are temporary is not to be diminished by it, but to be placed gently within a story far larger than any single life or world. The universe unfolds at its own vast and patient pace, and we are here to witness a small, bright chapter of it, which is no small thing. So we have followed the black holes to the very edges of what is known and imagined, from the exposed singularity that nature may forbid, through the structured interiors that theory proposes, to the slow fading that will, in the end, claim them all. Gathered together, the family spans a range almost impossible to hold in one thought. The hypothetical grains smaller than atoms, and the stupendous giants wider than solar systems. The starborn and the primordial, the feeding and the sleeping, the paired and the wandering, the exact shapes of the equations and the strange cousins at their edges. And all of them, every one, are the same simple thing, a place where gravity has closed over matter and the ordinary rules of distance and return no longer hold. What unites them is not their size or their behavior, but their nature. Each is a boundary, an edge beyond which the universe keeps its secrets, a region folded quietly away from all the rest. And though they seem the most permanent things in all of creation, they are not. On timescales beyond comprehension they will fade, the greatest of them last of all, until the universe has sorted itself back into the same profound quiet from which everything once emerged. And so we leave the black holes where we found them, folded quietly into the dark, keeping their secrets across spans of time we will never see the end of. There is no hurry here, and nothing left tonight that you need to hold. Let your breathing slow. Let the weight of the day drift off into that same soft distance. Sleep well, and good night.